Hello guys, so today I'll be solving this problem. So the problem states that maximum running time of n computers. So the question states that we have n computers and you're given the integer n and a zero indexed integer batteries where the ith battery can run our computer for batteries I minutes, okay? And you are interested in running all n computers simultaneously using the batteries. Okay, so basically we have been given some computers, okay, and some n computers like that, and we have been given some batteries, okay, uh, let's say some k batteries, okay. Now and what we need to make sure do is, so we have to so basically these computers draw some power, right? And when they are drawing some power, so we have those batteries as our power backups. So yeah, so all of these systems are connected, like we can connect all any one of these batteries to any of these computers. Now there are some condition over those batteries. So yeah, the first condition is you can insert at most one battery into each computer. So one computer can be connected to one battery only, okay. Then after that, at any integer time at any integer time moment, you can remove a battery from a computer and insert another battery any number of times, okay. So basically, let's say I have this and yeah, these two battery. So I can basically exchange these two batteries with these two computers, okay. This is one condition. Then the inserted battery can be totally new or a battery from another computer, okay. And you may assume that the removing and inserting processes takes no time. Okay, cool. So there will be no disconnection. That means, okay. Note that the batteries cannot be recharged, okay. So they can only be decharged, okay. We can only consume them. So yeah, then we need to return the maximum number of minutes you can run all n computers simultaneously, okay. So basically for every computer uh, we can first connect it to a battery, okay, right. So there is this, okay. For every computer I can have this kind of connection. Then there is like, okay, I can also exchange batteries, okay. So let's say so the batteries minutes that has given, so that will not be like always same, right? It can happen like the battery times are varying, okay. Some may be large, some may be high. I can get maybe a histogram like this, okay. Some may be high, some may be low, so something like this. So kind of a histogram of batteries, okay. And based on whatever batteries are my maximum, I can maybe start with them connected to my first initial computers. So and yeah, and in between those connection I can exchange those batteries and put them here, and I can remove this connection, maybe put them to some other computers. I can do all this kind of stuff. And they are saying that when we are doing this kind of switching, okay, so the computer is not getting disconnected, or basically it means that the computer is not getting switched off. So it is still running at that moment when we are switching out batteries, okay. So from that analogy, okay, batteries, yeah, we can do something like this. Like we can think of, like, there is a layer, okay, that is a constant power supply, okay. Since there is no disconnection happening when we are switching out batteries, or when we are like plugging in new batteries to a system, so there is no disconnection happening. So basically means that time and computers are still running, okay. So I can basically build a layer on top of batteries, okay, which will symbolize like this is a constant power supply, okay. Now I can say that this constant power supply is being powered up by these batteries. Okay. Okay. So it's not like all batteries are connected to the power supply at the same time. Whenever my I need my power supply to be like maybe set for to run for at least some t time, so I'll be switching out some batteries, but for the computer perspective they will be seeing a constant power supply. So yeah, I can replace all this battery to a constant layer. Cool. Now in this question, okay, so nowhere they have written that the computers are heterogeneous. Okay, so we can make a claim that all computers are homogeneous. Okay, so let's make a claim: all computers are homogeneous. Okay, now why did we make this claim? Okay, so if I make this claim like all computers are homogeneous, that basically means the rate of energy, okay, that they will be drawing out from my power supply, that will be constant for all of them, right? Let's say the rate of energy, each computer is consuming, let's denote it as P. Okay, now if I say that, hey, I want to run my system for, let's say, for some t time. Okay, that means all these computers will be consuming a net total energy of uh, P times t. Okay, where t is like this many minutes, like I need to run my all my systems at least, like not at least, uh, like this amount of time. Okay, I can say required number of minutes. Okay, so I am doing all this to get to a strategy. Okay, in order to how to find this maximum number of minutes. Okay, so for now I have said that, okay, the rate of energy each computer is drawing out power is P. Okay, or rate of energy each computer is consuming is P, and then my total energy will be uh, P times T for each computer. Okay, so for n computers it will be times n. Okay, so this will be my total amount of energy I need to provide to my computers. Okay, so that they can run all simultaneously for t minutes. Okay, now this is my demand, I can say. Okay, now this layer basically designate my supply. Okay, so because my batteries are the things which are like supplying their energies, okay, to my power supply. Okay, so I can say that if I want to run, okay, or if I want my power supply to be running for t minutes, okay, then I can basically check how much each battery can contribute. Okay, so if I have, let's say, B1, B2, B3, like that, let's say some BK batteries. Okay, so each B of I designates like the amount of time, okay, they can run a computer. Okay, so if I want my power supply to be running for t minutes, then that means I can overall consume minimum of my bi comma t. Okay, so if I want to run my if I want to run my like if I want to give supply for at least t minutes, okay, so for every individual battery, okay, I'll be consuming this, so I can consume at max this much times from them, right? So yeah, so the total amount of supply I can generate will be a summation of this. Okay, now this will be the total amount of supply I can give it to my power supply. Okay, so the total amount of energy I can give to my power supply will be this times P, because my power supply will be drawing out from the batteries at the same rate like the computers are drawing out the power, right? Because this is like a Fugazi layer, okay? It doesn't exist, okay? We are just imagining it, but as per the question, this power supply layer exists, okay? So yeah, so this will be my uh, total supply energy, okay? Oopsie, energy, okay? So in order to meet my requirement, which is to run this all n systems, okay, or all n computers for at least 10 minutes, my total supply energy, okay, that should be at least the total demand energy, right? Now if I compare these two expression, so this will become P times summation of minimum of each battery's contribution, okay, let's call it times, it should be greater than equal to whatever demand equation I have, which is P times T times N, okay. So now it's basically a inequality like solution. So if I see this, so here P is like a common term, okay, so I can cancel these out, okay. So I will have a relation that the summation of mean of Bi comma T, it should be greater than N times T, okay. So this is a relation that I am getting when I am comparing my total supply energy with the total demand energy, okay. Now if you look at this, okay, or maybe you can look at this, okay, this basically give you an intuition that if I draw a plot, okay, where I'm saying if I want to run for t minutes, okay, so the amount of energy, okay, so basically if I look the curve for this, okay, the total supply energy I can generate, okay. So this curve will look something like this, okay. Let's say this is my total supply energy, okay. So initially, let's say if my T is less than, let's say, the smallest B of I, okay, if T is less than my smallest B of all i's, okay, so this will grow like this, okay, because here what will happen, so minimum of Bi and T, it will give me the it will basically give me this equation. So total supply energy, this will be the number of batteries I have, okay, times T, because for every comparison with Bi to T, this will give rise to T only, because T is smaller than the smallest of Bi, okay. So for total number of batteries, this will be the summation and this will be times P. Now if I plot this curve with respect to T, so this will be Kp times T, okay. So the total energy curve will be so this is similar to our line equation, like, so if I take this as y and this I take as m, okay, and this I take as x, so this is a linear chart basically, y equal to mx. So here we don't have intercept, okay, so this will be this kind of a relationship, okay. So yeah, this will increase linearly just like a line, but as t goes to some intermediate values, okay, where t is let's say between the max B of I to mean B of I, okay, so now this will not be linearly proportional to y, okay, because at some point of time T will be less than, like, greater than my B of I. At that time I need to take B of I, okay, when I am doing my total energy calculation, okay. So that time T will not be linearly, or maybe there is, so you can think of some offset will be added, okay. So that time this equation will be something y mx plus some constants, and this constants will be some summation of some B of j's. Okay, those j's are like lesser than my t. Okay, and for any j who is like greater than my t, so yeah, those will be basically computed to t based on my mean of bi and ti. Okay, so this will be revolving around some smooth curve. Okay, so the rate of increase will start to become saturate. Okay, now when t becomes extremely large, okay, so that time, or I can say when max of bi becomes smaller than my t. Okay, so at that time this curve will saturate. Okay, so because at that time what will happen is, so the total amount of time, okay, I will be getting, that will be basically my p times uh, summation of b of I. Okay, when t goes like above max of bi. So yeah, so you can think like, now you can see like my total energy supply is becoming saturate, so which basically means I can, so I have a upper limit. Okay, on the amount of energy that I can generate, right, from the batteries. Okay, now from this you can think of something like, so since this thing will get saturate, okay, but if I check my demand energy, okay, that will increase with respect to how my t is increasing. So the nature of transition in this relationship will be something like this. Okay, so let's say I plot for t. Okay, so at smaller values of t, okay, so this thing will be small. Okay, and it may happen I will be like let's say I will be meeting my total demand energy. Okay, so but at larger value of t's, okay, my required energy or demand energy will shoot up, whereas this guy or my total supply energy will get saturated to this value. Okay, which is like p times summation of bi. Okay, so during that time, so I will get a pivot point. Okay, so initially at small values of t, okay, I will be like meeting my supply energy with demand energy. Okay, yes, yes, but at one point of time it will happen that my supply energy get saturated, or maybe I'm at like this stage or this stage, or it may happen I'm not at all satisfying it. It may happen. Okay, but yeah, so eventually I will get a pivot point where at with increase of t I cannot meet my demand energy with the supply energy I have. Okay, so all this will be converted to no, so I cannot match, I cannot match, I cannot match. Okay, so yeah, at that point we basically need to return at which point, let's say t, okay, we can go at max, so that our supply energy will be like greater than equal to my total demand energy. Now you can think of, so this is like a uh, so right, so now you can think of, so now I have a search space for d. Okay, so my t, let's say it can vary between, let's say 0 to maybe infinity. Okay, so if I am creating a search space for my t, okay, I can reduce this infinity to the maximum time the batteries can contribute, which is basically the summation of bi's. Okay, so in this search space, okay, I can easily find my pivot point using a binary search kind of approach. So how this will be happening is, so initially how it will look like, okay, I have, let's say in this zone I have all yeses, so let's say this is a t line. Okay, so in this zone, so all my t's are satisfying my like at all these t's my supply energy is greater than my total demand energy, so all this will be true. And at after this point all these are no's. Okay, my supply energy is not meeting my demand energy. Okay, so if I do a binary search, okay, between these points, okay, so this point it's, let's say 0, and this is my upper limit, let's say this is summation of bi. Okay, So if I do a binary search, let's say if I'm at this mid, okay, let's say the binary search gave this, okay, so I'm at this zone, okay. So if I check with this t value, okay, and I calculate my net demand energy, okay, so this will satisfy, okay. Then what I will do is my search zone will reduce from mid to uh, yeah, let's say mid to this point, okay, mid to this point. So this is the point, let's say this is my answer, okay, because after this I am having no's, and this is the max t where I'm getting yes, okay. So I'm just showing you how binary search will help, okay. This is my answer and this is like b of I, okay. Now let's say I again do a binary search over this search space, okay. So I will get a midpoint around here, okay. Now at this point I'll be calculating my total demand energy, okay, and I'll be comparing with the total supply energy I can generate. So at this point this is in the no region, okay, so this will give me no. So I'll be reducing my right boundary to my mid -1 to here, okay. So yeah, now this will look something like this, okay. So let's say this was in my first iteration mid 1, and this was in my second iteration, let's say mid 2, and this is like mid 2 -1, and this is like mid 1, okay. So mid 2 -1, mid 1, okay, and here is somewhere answer, okay. So eventually using binary search, it will happen at a time where I'm touching my answer, okay, and this I'll be doing with the log of my maximum size of search space, which is log of b of I. So yeah, so that's the overall idea, okay. So just start with calculating this supply energy, okay, and compare with the total demand energy with respect to t, okay. And using binary search we will find a pivot after which we are not at all meeting our supply like demand energy requirement. So yeah, so I'll be first coding it up in C++, so let's do it. So I need to return long, so let's create a alias for my long. So I'll say define ll long, okay. Then I will, let's say, create my answer. So one answer is always 0, and finally I will be returning my answer. Then I'll be creating my search space. So I'll say L equal to 0, R equal to my summation of all the batteries, accumulate batteries begin, yeah, let's do this and let's do this, yeah, batteries end 0 ll, okay. Then I'll be doing a binary search. I'll say while L is less than or equal to R, okay. And oh yeah, so this is for my search space, but in that I'll be calculating my demand energy, okay. So that will be an iteration over the number of batteries I have, okay. So yeah, so this will be the number of batteries, let's say that is k, okay. So this iteration I'll be needing to calculate my total supply energy, okay. So I will just show you in the code how it will be happening. So yeah, so here I will say my current t is L plus R minus L, so standard binary codes, binary search code. So t, now I will say I will compute my total supply energy, okay. I'll say total supply energy I can generate, let's initiate to 0. Then so yeah, I'll be basically using this relationship, okay. So yeah, then I will calculate my total supply energy, where I will like iterate over all my batteries, and I will increase my supply as this, so long or maybe 1 times long times minimum of the batteries I have, so T and B, okay. So basically I'm doing this summation, and finally I will check with this relationship. So if my supply total energy is greater than equal, yeah, this is C++. Yeah, if supply total energy is greater than equal to my total demand energy, which is like n times or 1 times n times t. Okay, then I will update my answer to my current t, and I will try to search on the right of my current mid value. So I'll increase L to t plus 1. Otherwise, if it is not meeting, okay, I need to search on the left. So I will decrease, change my R. I'm not sure why my computer is lagging. So I'll change my R to t minus 1. Okay, and yeah, after that I will finally return answer. So let's check with all the test cases. And yeah, we got a error, so let's fix it. And yeah, so let's run it again. Haha. Okay, so what is happening? So t is long, b is not long, so let's do it here and let's change it here. Yeah, so this should work now. Okay, all test cases passed. Let's submit. Cool, successfully accepted. Now let's do it for Golang. Okay, so maybe before that I can discuss on the time complexity. So here I actually started with the time complexity calculation. So yeah, in the C++ code, if you see, okay, so basically I'm doing a binary search over my search space. My search space size is the summation of b of I. Okay, so this is my search space size. Now at every iteration in my binary search, I'm doing a number of batteries iteration, right, to calculate my supply energy. Okay, so yeah, per iteration in binary search, I'm doing a k batteries traversal. So yeah, my overall time complexity will be big O of summation of bi times k, and you can see like I'm not using any extra space here. Okay, so my space complexity will be constant. Okay, cool. So with this, let's now code our Golang. Okay, so I'll start with answer. So I'll say answer is int64. I need to return int64, that's why. Then I will say L is my int64. So this will be 0, and my R is int64. This will also be 0 because I'll be increasing to the summation of batteries. So I'll say I will update my R as batteries in range batteries. Okay, so I'll increase my R to int64 of B. I'm not sure what's happening. Okay, then I will perform the binary search. Okay, so first I will calculate the t. So t will be L plus R minus L by 2. Okay, and here I can, oh, my computer is lagging, I don't know why. What am I running? Okay, so var int64. So I'm taking this in 64 because I'm doing a division here. So yeah, this might happen, like it might happen t is becoming float. So yeah, this will always convert it to int 64. So yeah, after this I will calculate my supply energy. So I will say my supply is also int 64 initialized to 0. Then I will iterate over all my batteries in range of okay, it's not my day, I guess. So I'll say okay, supply plus equal to mean of int64 converted b and my t. Okay, then I will say if basically I'm doing this condition, right? Yeah, then I will say if my supply, okay, is greater than equal to my total demand energy, so which is int64 converted n times t. Okay, then I will update my answer to t, and I will search on the right whether I can get some better t value. So I will update or maybe I can do this here, t and t plus 1, and else I will decrease my right to r equal to t minus 1. Okay, and finally I will return else. Okay, let's first do a proper indentation. Okay, so here, yep, it goes here, and I have this, and this guy will come here. Oh yeah, this guy will come here. What is this for loop? This for loop ends here. Oh yeah, this will go here, with this comes here, and this comes here. Okay, yeah, cool. Now let's run it for test cases. Cool. Yeah, all test case passed. Now let's submit. Is it recording? Yeah, it's recording, right? Yeah. Cool. Now let's finally do it for Rust. Cool. So I'll be creating a mutable variable for my answer. So let mut ans let mut ans 0 as i64. Then I'll say let mut l also as 0 as i64. Then I will update my r to the summation of all the batteries I have. So yeah, first I will initialize at i64. Then I will say for battery in my batteries, so r plus equal to b as i64. Okay, then I will do the binary search, r. Okay, and finally I will return my ans. Okay, so I will create my t. So t will be I can say i64 here. I64, I will say l plus equal to r minus l upon 2. Okay, then I will create my I will calculate my total supply energy that I can provide. So supply will be 0 as i64. Okay, then I will iterate over all the batteries. So for b in reference of batteries, so supply plus equal to oh yeah, I need to use comp, so I'll say std comparator. Okay, so I'll be comparing my minimum of my batteries as i64 with my t. Okay, and in the end I will checking whether my total supply energy is greater than equal to my total demand energy, which is n as i64 times t. Okay, then I will update my answer to t, and I will search on the right of my mid. Okay, so I will increase my l to here, and then I will otherwise, if supply is not meeting my demand energy, I will decrease my r to t minus 1. Okay, so yeah, I think it should work. Yeah, it worked, and now let's submit. Cool. So all 3 languages done, and all test case pass. So yeah, this was the core idea. Okay, so the thought process was like, since those exchanges were not disconnecting the computers, and at the time of disconnection all computers are running like at the time of like switch, all computers are running simultaneously, so we can thought of this power supply. Then from that we just apply some minor physics concept to calculate this total energy, and then we just compare our supply energy with the total demand energy. Now our requirement is like supply energy should be greater than equal to my total demand energy, and based on that these power terms got cancelled and we got this relation. Okay, now this is just the explanation for the nature of T with respect to the total supply energy. And yeah, finally we will get this kind of transition, where we can get a pivot for T, where my supply energy can, like, this will be the maximum point where my supply energy will always be greater than my demand energy, and after that everything will fall off. Okay, my supply energy cannot be more than my demand energy, so all this value will be no. And yeah, with that we just did this search space calculation. Okay, and I just showed you like how to do a binary search to get it. Okay, so yeah, so if you guys have still some confusion, so I will say like just run a test case on your own. Okay, so I didn't run any test case because I thought like by telling you all this stuff to you guys, that will give you some intuition. Okay, and then you can think of this intuition in terms of test cases. So yeah, just so you can feel free to like comment in the video if you have any doubts regarding this description. But yeah, if you learn something new and if you like this video, so please do subscribe to the channel, and you can press a like button to the video, so that will motivate me to create new contents. So yeah, just stay tuned to watch more videos. Thank you. Bye bye.